record on this computer. Yeah, there we go. You might have gotten a pop-up saying like recording is started or something. Hopefully that happened. So, well, yeah, welcome to the workshops. We have these every Sunday, so I've planned to have them every Sunday at 11 a.m. And we have like a 2-hour time block. Today it might not take 2 hours, maybe it will. I tend to go on for a long time and try to cover as much material as possible usually, because the course itself is pretty fast-paced, so I try to like review and have you keep up to date on all of that. So yeah, I'm planning 11 a.m. Eastern time to 1 p.m. Eastern time every Sunday. So presumably if that time doesn't work for you, you're probably not here right now and you might be watching this as a recorded thing. But if that time doesn't work, then Michael, who's another workshop leader, he was actually, he took the workshop with me last year. So like when I ran it last year, I had him as like one of the students, which is cool. He's really great. You should, he's great. If you can't come to my workshop, go to his. I'm sure he's going to be fantastic. Yeah, so if you can't make it to this, then his runs from 5 to 7. I sent the Zoom link for that with the Canvas announcement like yesterday. So you can always go to that one. Yeah. So like I mentioned, I also ran this last year. So I, did 3/4 of the year in person and then 1/4 of the year off person. And when I did that 1/4 of the year off online, last year I was like, at least I like to think that I was pretty on top of it. I was kind of prepared because, as you'll see, I have this like drawing tablet thing that connects to my computer. It's kind of like how most professors now use iPads, except I kind of like this one a little bit more. But yeah, so I was like way ahead of the game, and then now every professor's had their summer to like order their iPads or something. So maybe what I'm doing might not be. Maybe I'm a little bit outdated at this point, but what I typically did last semester was I would share my screen and, well, why don't I even actually do that? Oh dear. Oh, okay, the share screen. Why is it green? Okay, it's a totally different color. All right, and oh, there we go. Okay, hopefully you should be able to see this window here. And what I'm able to do is draw on here like this, and I can say like hi, and draw a bunch of stuff, right? And I think this is really good because organic chemistry is like a really visual subject, right? It doesn't work to see organic chemistry on a PowerPoint. Like it's, part of the whole process is you actually yourself have to draw things on the paper. And well, if you don't ever see anyone do that, then how are you supposed to learn to do it yourself? It's going to be way harder, right? So for me, this worked out really well, and it seemed pretty smoothly to transition from actually drawing on boards in the classroom and, doing it here virtually. Yeah, I use this like PowerPoint sort of program. I'm by no means an expert at PowerPoint. In fact, I'm really terrible with it. So there might be some times where I'm like I like have technical problems and just can't, or like I'll take like a minute to figure it out or something. But for the most part, I'm pretty, I'm able to work with it pretty well. And also, as you could tell, I didn't use Zoom last semester either. So Zoom is also a little bit new to me, but I've, like everyone, I've had some experience with it. So yeah, we'll figure that out. Okay. And then the one last thing I wanted to say before we actually get to chemistry, because of course that's what this is all. Oh wait, one more note about Zoom. So I have two like monitors here. So over here where my camera is, I normally keep the chat open, and yeah, so I normally keep the chat open, and I could keep the participants tab open too. Well, last semester I didn't use Zoom, so I didn't have that. But yeah, I can keep those open. And so if you like send chats or something, like questions in the chat, then oops. yeah, if you send questions in the chat or something, then I can try to answer those, like, because I'll see them over here. So I'll glance over here every once in a while, but over here, which is where I'll be looking most of the time, is where I actually draw. So, you know, when I'm like drawing, I'll be doing this. Okay. Okay. Now, yeah, the actual last thing I wanted to mention before we get to chemistry, because that's what this is all about, is the fact that this class is not easy. And well, it's hard for me to say whether it's going to be easier or harder in the format that it's in now, but it's not going to be like easy overall, right? Like it's a pretty tough class. I mean, there's a lot of material and it goes through it pretty quickly. So I was looking around the Canvas and I saw that like the way that it kind of works is that there are these like recorded lectures by Professor Molander, which is, well, that's pretty good because I took the class with him. So like I was watching some of those lectures and I mean, they're exactly the same as my notes from 2 years ago. So that's pretty good. And he's a good lecturer, but yeah, you have these like pre-recorded lectures and then there's this like in class time where you, I guess, ask questions and do problem solving, right? Which is good, but it's still fast paced. It's still like a tough class. It might be stressful. I mean, you don't have everyone else around you to amplify that stress, but like there's a lot to cover and organic chemistry is a pretty notorious class for that. So I wanted to say that, and I'll probably say that very frequently and like constantly be emphasizing that because like maybe for you it won't be stressful, but for a lot of people it's a tough class. And well, my whole purpose here is to make sure that it's not as like crazy stressful and that you feel like you're more able to stay on top of what's happening. Okay, so that's what I'm here for, is to make sure that you know, you don't feel like you're wildly falling behind, or to remind you and push you to say like, push you to, you know, review this whenever, or like practice these problems or something like that. Okay. All right. There are, okay, let's actually get to chemistry now. Every week we'll be working on some like worksheets, like practice problems. In my great wisdom today, I totally forgot to send the links to those. I can actually send it in the chat. Last year I had a pretty like good system for distributing all of these things to everybody, but for now it's just on this Google Drive folder. This will be the Google Drive folder that I'll be using, and I'll be keeping it up to date, but I totally like forgot to send this out in the email or whatever. Yeah, so we'll be using the worksheet there under the folder W1. That's for week 1 or workshop 1. It's the same thing. Yeah, the workshop isn't there. It's a few problems. We'll get to those. What I started doing last year, which I found that a lot of people found helpful, was that I would, at the start of each workshop, I would actually like review. I would, you know, talk about, there's a lot of material each week, right? And some of it is definitely more important, or you should be keeping in mind a little bit more than other things, right? So I usually like to talk about some sort of review, or give like an overview and throw in some problems and talk about it first. Okay. Eventually for these problems, maybe I'll try breakout rooms. I haven't worked with breakout rooms too much, and I don't know what people's personal opinions are. Maybe I'll send out a poll at some point and ask, but for now, let's talk about chemistry. Okay. Maybe I should pause and ask if there are any questions about non-chemistry related things before I actually get into it. Okay, I don't see any reactions in the participants panel. And oh, okay, yeah, there we go. We did get a question. It takes a moment to type. Will I post answer keys? Yes, I will. Okay, I will post both like the solutions and like answer keys for the worksheets, and I'll also post these. Oh God, my handwriting is. I'll get back to it. Oh geez. Okay, I promise I have better handwriting than normally. Okay. yeah, again, I haven't, I've taken the summer off for sure. I haven't taught any organic chemistry during the summer, so uh, there's a reintegration curve or so. Will the recordings be made available for later viewing? Yes, they will. Yeah, the recordings, I'll be posting them. I record them last semester. I uploaded them. I have like a YouTube channel where I just put a bunch of organic chemistry videos. Last semester I uploaded them there, and I'll do the same. Well, I'll probably do the same this time. I might also put them in like a more like official place than my personal YouTube channel. Like, yeah. Okay. Can you remind me where the worksheet can be found on Canvas? It's not on Canvas yet. I haven't uploaded it to Canvas. Last semester I made a folder on Canvas and uploaded them there. I haven't done that yet. Instead, there's this Google Drive folder that I just sent in the chat where the worksheet is. I'll also be pasting the problems onto the screen so like you can see them. I don't know how to use Photoshop that well, but I know how to use it well enough to do that. So I'll do that, and we'll probably mostly be working through the problems together, like for this first week. And that's what I did mostly last semester, and it worked pretty well. So yeah, if you like can't find the worksheet, or if the I think the Google Drive folder should be working, but like if something's up with that, it'll probably be all right to follow along with what we're doing. Other workshop worksheets the same for all sections of the class? Yes, they are. For Professor Kallander, for both mine and Michael's workshop sections, they'll be the same worksheets. There are other workshop leaders who are for the other professors, so I totally don't remember who the other professors are. I've forgotten, but I think Professor Molander is one of the other ones. I think he follows exactly the same schedule. And then you probably don't want to go to the Chem242 lectures or workshops. That would be a bit much. So yeah, I think the worksheets they'll be the same for each workshop. Okay. And I see no other questions or no other reactions in the participants panel. So how about we get to chemistry? Okay. All right. So I'm going to be using the screen sharing thing now. So if you want to like adjust your screens or whatever, this would be a good time to do it. Okay. So this is for workshop 1, and the course covered, if you follow the book, it covered chapters 1 and 2. All right. And those chapters cover structure and bonding. And the second one covered, this is probably the one that, well, chapter 1 is important. Chapter 2 is where you can really ask problems and try to, and start to do things. This one covers acids and bases. Arguably the most important concept in both semesters of organic chemistry. So they're kind of putting the big stuff up front. And then you also got functional groups. Functional groups might have been in chapter 1. I don't remember. Either way. You got, these are the big concepts that you got up till now, right? From what I was looking around in the pre-recorded like lecture videos, it seemed like structure and bonding and functional groups kind of came first, and then you went up to resonance, and then you did acids and bases, right? That's like the pretty standard way of doing it. The textbook order is kind of like iffy. So yeah, this is what we went with. Yeah, so in terms of the lecture videos, it really started with functional groups. Okay, and well, I'm not really gonna sit here and remind you and draw all of them out because like there are tables for that, right? What I will tell you is what's important with functional groups is that you've got to learn them. Okay. Yes, there's like a long list of them. Yes, it's kind of memorization, but you really need to know the functional groups. There's a lot of there's a bunch of them, and they're really what you can do reactions with, right? If you take something that's just purely made of carbons and hydrogens and only single bonds, it's pretty useless. You can't really do a lot of chemistry with it. You can do one thing of chemistry with it in the entire course, which you will, that's like the first reaction you'll learn about. But otherwise, you need either like double or triple bonds or some other kind of atom in order to make chemistry interesting. Okay. So yes, learn the functional groups. Each chapter of the course, or like each kind of section of the course, is usually themed around one functional group. So early on, the first you'll kind of get to see is like halides. So when you have a halogen on hydrocarbons, that's like probably the first big one that you'll see a lot. And then you start to see things about double bonds, triple bonds, eventually alcohols. And then like the whole second half of organic chemistry, like Chem241, is really based around carbonyl groups. So C double bond O groups. Yeah, now is the time to like get to recognize these functional groups. Besides the fact that a typical like exam problem, although you guys have slightly different format exams or assignments, a typical problem for like the very first exam is here's a big molecule, name the functional groups, or at least name some number of them, right? So we'll see some of those. That's like a super standard sort of thing to ask. Okay. Of the functional groups, and this sort of falls under here, a kind of general idea about them is that you should be able to recognize like the hybridization involved. Okay. So for hybridization, there's like, you can talk about hybridization for like ages and hours, but the kind of important part is that it's what lets atoms actually bond to each other, or at least what lets covalent things bond to each other. So, you know, things can hybridize to be either sp, sp2, or sp3. Okay. An example of each would be like sp3, you can have methane. Okay. This guy is called methane. Is just like a common name. That is good to know. sp2, let's see, what would be a good example of an sp2 thing? Well, I already brought one up, right? C double bond O. And then whatever, we'll put H's here. Okay. So we're talking about these carbons in particular. And then for sp, the main thing you'll see is sp3 is C triple bond C. Okay. And there we can put an H there or something, right? And yeah, whatever. Let's put another H here. Okay. So both of these carbons now are sp. All right. I did these, all three of these, in terms of carbons, but you can also do them in terms of other atoms, right? Oxygen and nitrogen can also be hybridized. They, in fact, have to be hybridized to make bonds. So, like, if we just went with this and said, like, okay, well, what about water, right? Here we go, right? Water, as it turns out, is sp3 hybridized. Okay. And there's a very simple, like quick and dirty trick to recognize what the hybridization of something is. And that is how many separate things are attached. All right. Let me put this in red. All right. So for each of these, you can see that like these carbons each have 2 separate things attached, okay? This carbon has 3 separate things. This one has 4, okay? This oxygen has 1 hydrogen, 2 hydrogen. Maybe I'll put this in blue. I like being able to use different colors. It's kind of nice. So 1 hydrogen, 2 hydrogen. And then it has a 3rd thing, which is this lone pair, and a 4th thing, which is this other lone pair, okay? So lone pairs count as their own thing. And this rule is kind of, it makes life way easier because every once in a while, someone will be really mean and they'll say like, oh, what is the hybridization of like BF3, okay? And if you remember, boron has this like awful annoying rule where it breaks the octet rule, and boron like this is totally happy, okay? Well, you don't even need to think about it. There's 3 fluorines attached. There's no lone pair, right? So this is sp2. Okay. Saves you a little bit of work. All right, cool. That was plenty to talk about hybridization. That's like a kind of standard thing to ask about, which is just name the hybridizations of these atoms. All right, oops, there's this thing down here, but I'm gonna move this way down. Oh, geez. Okay, you can already see that my Photoshop skills is pretty bad. Okay, that's okay. So yeah, we have this stuff about hybridization. Oh, let's see. Oh, somebody's asking a question about like hybridization geometry. So they usually say sp3 is tetrahedral. Yeah, there are other kind of hybridizations. In general, tetrahedral, so you can say something like water is also pretty, you typically wouldn't say this because the atoms are, well, okay. When you refer to the geometry previously, like in Gen Chem, it usually refers to where the atoms are, right? But if you look at water, it will still be tetrahedral if you think about each of these 4 things, right? Electrons and hydrogens and other different atoms take up different amounts of space, so it's never going to be like perfectly tetrahedral, but like these 4 orbitals for each of these things will be roughly in like a tetrahedral arrangement, I guess. Yeah. Okay. Yep. All right. So, and then just to, can I erase this thing? Oh yeah. All right. Let me make this huge and just get rid of this. Okay. Yeah. So for functional groups, there's like a little bit to mention, and I'll just mention it really in terms of halides because otherwise the rest is pretty much just remember the names of them. Okay. So for halides, which are kind of the first that you'll get used to, if you have something that looks like this with iodine on there, okay, if it's attached to a carbon that's attached to one other carbon, this is called primary, or you can write it with a 1 in a little circle like that. If it's attached like this to a carbon with 2 carbons next to it, it's secondary. If it's attached to a carbon with 3 carbons, it's tertiary. Okay, that's kind of all that there is to that. These 3 things will react differently, and that's why this is kind of important. Okay. You can also have a few special cases. So if it's attached to a methyl group, which I'll call that, okay, and a methyl group looks like this, okay, and it has the iodide on there, okay, this is called methyl. This is a methyl iodide, okay. 2 more examples. So if it's attached to this special ring, which is special, but you don't get to do anything with it for the entirety of this course, this is called benzyl. So it's attached to a carbon, which is attached to this ring here, which is like on its own, it's called benzene, but attached to something, it's called phenyl. This sort of arrangement is benzyl. And then 1 more, if it's attached like this next to a double bond, except 1 carbon away, this is called allyl. Right? And these will matter a lot when it comes to doing reactions. Okay. But for now, they might just ask you about like, oh, you know, what is described as iodine, and it's like for primary or something. Okay. All right, cool. And well, I'll skip the rest of the functional groups. Again, there's like a list or table of them in the textbook. There are lists online. I was looking around for some good ones and I couldn't find any great ones online. So I guess just stick with the textbook. Yeah. All right. And okay, that would be it for that. And just like a quick note about Lewis structures, which I already started to draw. I actually started to draw these other things. Okay. So just a note about like structural drawing. In Gen Chem, like you're used to drawing Lewis structures. And you usually draw them as this sort of thing. Okay. But if organic chemists had to draw this for every single thing that every compound that they work with, like they would never get anything done. Okay. So instead we use skeleton structures. Oh dear. So we use skeletons. And so for example, we only draw lines in where there are bonds. And if it's a carbon, it's just an intersection. And we don't draw in any hydrogens, so you're kind of expected to just fill in with the hydrogens. All right. It is certainly good and worthwhile to get used to these. A typical question that they might ask is like, here's some big structure. It's drawn in as a skeletal structure. What is the molecular formula? That is like, okay, if you take this very basic structure here, then this thing is the same as, here's all these hydrogens. Okay, there we go. Okay, it looks like that. And all right, now it's pretty easy. We can just count, right? So 1, 2, 3 carbons, so C3. And then if you go around and count the hydrogens, you'll get 8. All right. This example was relatively straightforward, but if they give this to you on like an exam or well, I guess one of your quizzes, right? It'll probably be a more serious example. It'll be something larger, right? In past examples, they've used like, well, way bigger things. It's typical for them to take like some commercial drug and just say like, oh yeah, what is the formula of it, right? Best way to do that is actually just, you don't have to, I mean, you don't necessarily have to write these carbons, and drawing the whole structure out over again, like from scratch is kind of hard, and there's a lot of room to screw up there. But if, let's say you're given a structure like this, what I've done in the past is just take what they give you and then fill in the hydrogens. Okay. So that's one way to do it. This is how I've done it in the past. It saves you the time of going through and drawing it over. There's less room to mess up. And then you just have to worry about counting your carbons, but that's just at these intersections. All right. And the important thing if you're doing this, or in general, whenever you're drawing any structure, is that carbons, it never has 5 bonds. Okay. This is like the most common error, right? And a lot of you might be coming out of Gen Chem and you're like, okay, yeah, that's like, obviously I knew that. This happens a lot, like way more than I can emphasize. Once you get to the point where you're drawing like a million structures on the page and there's arrows flying everywhere, right? Electrons are going crazy. It's really easy to overlook the fact that there are 5 bonds on a carbon, like super easy, right? You can just like, it's totally normal to just draw something that looks like this, right? Like here's a double bond and here's an O or something, right? And you don't even think about it. But this is not okay. You cannot draw this, right? It is illegal. It's not good. Yeah. Let me erase. Here we go. Okay. Yeah. erase it so that you never draw 5 bonds. You don't even think about it. Okay. Yeah. All right. And maybe the kind of like, well, now that we have Lewis structures down, we can get to like really the important stuff and where things get challenging. Oh, look, my cat came. I'm not gonna pick her up and bother. Okay. Now where things get like more challenging and where the real problems come in is when you have to start drawing resonance structures. Okay. And resonance structures are super important because they also affect acid-base problems. Okay. In fact, in terms of acid-base problems, the most that you're probably going to get are having to do with resonance structures. All right. So the rule here is that you can only play with things that are either a double bond or lone pairs. Okay, you can't play with anything that's sp3 hybridized. You're not allowed. sp3 hybridized things have nothing to do with hybridization. They're totally unrelated. Okay, so you can only play with double bonds, well, or triple. You could do triple. Or whenever you have lone pairs. Okay. So, for example, this is where, okay, now I'll actually start doing problems and like showing examples. Not necessarily from the worksheet, but this is like a very important problem that you'll see again in 6 or 7 months. So here's a question. So like, let's say you have these 2 compounds and you don't need to know anything else about them besides their structure. So let's say you have that, and well, here's another one that looks exactly the same, except, oops. Now this group over here, this ketone, is next to it, right? And on each of them, there's this positive charge. Okay. So let's check I drew everything right. Yeah, I don't see any things with 5 bonds, so okay, we're at least fine there, right? But the question is, which of these 2 is more stable? Okay. And well, I'm talking about resonance, so you probably figured out how to solve it. So you should draw out the resonance structures, okay? And what you'll find is that on one of these 2, you'll be able to resonate with this carbonyl, so you'll be able to use this double bond and get more resonance structures. And on the other one, you can't, all right? So in general, the thing with more resonance structures tends to be the more stable one. And if you do it out, well, it's this one. That's more stable, okay? The actual position of the carbonyl will matter. So this structure over here on the left will be more stable, right? Again, you'll see this problem down the line, like, well, sort of way down the line, but this will like wind up being a very important phenomenon once you start being able to do reactions on what are called aromatic rings. But that, okay, whatever, that comes way down the line. More importantly now is that you can actually use this stuff and talk about acids and bases. Oh geez. I promise I'll my handwriting I'll get back, it'll improve as I get back used to this. Okay. So acids and bases are kind of the big thing that you've learned now, and for like that first quiz or maybe the second one, the part where they'll actually ask you reactions will have to do with acids and bases. So although you don't learn your first like real reactions until like a few chapters down the line, you do know enough to work with acids and bases, so you'll be expected to kind of be able to do that. All right. For acids and bases, like I know I personally hated these problems when I did them, because like honestly, I think they kind of expect you to know a lot of knowledge that you're supposed to learn way later on in the course. And then they're just like, yeah, what do you mean you don't know what an electron withdrawing group is, right? Like, what? So these are hard problems. I wasn't very good at them when I first started them. As you go more through the course and you really like build an intuition for organic chemistry, you'll start to see like, you'll start to be more familiar with this sort of stuff, right? You'll know more about like what donates or withdraws electrons, and you'll be able to see what resonates like or what doesn't, maybe more quickly than you are already yet. Oh, okay, yeah. So Amy's asking for the previous thing if I could actually draw a resonance structure. Why don't I do that? Yeah, that's probably a good point. So with resonance, you can actually do like arrow pushing. That's like kind of the term for it. So whenever you draw arrows, you're able to move electrons around. Okay. So for this structure here, we're able to take this double bond and we can move it over to where this positive charge is. Okay. Oh, I guess I said lone pairs. I should have also said charges. Yeah, so when there are charges, you can also like move things around, right? Because there's an empty pi orbital in this spot here, right? If you like, you can also say like, we have one hydrogen here and a plus charge. So that means that this is an sp2 carbon, which means there's a pi bond that's empty. Sorry, a pi orbital that's empty, right? So let's move the electron over there. And with resonance, we use these double-headed arrows like reactions, well, unlike reactions, okay, to show that it's the same structure, it's just resonating. How about I use a different, what I just used black? Okay, so now we get everything else stays the same. There's that hydrogen and okay, all of that, right? And now the positive charge moves over here, right? Because previously on, let me use this blue. So on this blue carbon, there was previously 1, 2, 3, and 4 bonds. And now there is only 1, 2, and 3, right? So it's missing something, so there's a positive charge there. All right, and okay, so that is 1. And now just, now we're kind of ready and we could just run through the rest. And here we go. Oh, did I, oh, maybe I drew this, maybe I chose the wrong structure or drew it wrong or something. Okay, well, okay, so we have this, and now we have this positive charge over here. Oh dear. Yeah, it's totally not more stable, isn't it? Okay. Thank you, Amy. Okay. So, okay, so maybe for the moment, disregard that I said that this one's more stable. Yeah, I'll think about this a little bit more. Yeah, it should be this position that's more stable, but maybe I totally just screwed that up. Or I drew my bonds in the wrong place or something. Whatever, that's okay. So yeah, in this case, I've drawn all of the resonance structures that we have available here. So this is all 3 of the resonance structures for this compound. Okay, and yeah, thanks for pointing that out. Yeah, like I kind of mentioned, yeah, every once in a while I'll like miss something or something, right? So if you're following along and you see like something comes up and you're like, oh wait, no, what the hell are you doing, right? Then like, yeah, tell me. And yeah, I mean, we could think about it, or like unmute yourself and just be like, hey, you're like, what are you doing? There's no problem at all. Okay, yeah, I'll think about what happened here. Yeah, that's okay. All right, whatever. Let's just keep moving on. Okay, so for acids and bases, the thing that I'll say, acids and bases, okay? In the past, a lot of people have tried to ask me like, oh, they give you in lecture this like list of things that's relevant, right? Like things that affect acidity. And a lot of people have sort of asked me like, what, how do you compare things, right? Like, what is the order of priority? Like, how do you determine uh, what makes something more acidic or less acidic than another factor, for example, right? And then the really unfortunate answer, which like breaks people's hearts, is that like there's not really a clear order to how they go in, right? You can try to sort of write one, but like each factor affects a different compound or molecule differently, and yeah, it's like hard to say exactly which one will affect more than the others. So if you were to write a list, and this is like a rough list, this is by no means the the true order, right? Each thing will affect each different molecule differently. Um, so if you were to write a sort of list, maybe what you would say is that like, well, first thing that affects acidity would be like charge. Okay, probably charge, right? If something has a proton on it, it's going to be more acidic than not, right? If you have like a nitrogen that has a negative charge, it's going to want to take a hydrogen off something. Okay, so for example, charge is one thing. Okay, um, yeah. So after that is probably like what it can probably be like what different atom you actually have, right? So I'll just write like the atom, or you might call it like electronegativity. Okay, so for example, like nitrogen is way more basic than oxygen, um, which has to do with electronegativity. You also have that, for example, like if you have like hydrogen iodide, HI, or hydroiodic acid, I guess, that's a lot more acidic than, let's say, hydrochloric acid, because iodine's really big, and so it's like, let's say, easily polarizable, or like that's a pretty polar bond, so it comes all apart a lot easier. Okay. Um, yeah. Uh, so after that, you can probably get hybridization. All right. Um, which is to say that things that are like, for example, sp3 hybridized things are the least acidic. sp3 hybridized things are the most basic. Okay. Acidity and basicity usually work opposite. All right. And then after that, there is resonance. So the different resonance structures of something, the more resonance structures that the conjugate acid or conjugate base has, the more basic or acidic they are, respectively. And then after that, lastly, there's this thing that you hopefully saw in lecture called the inductive effect. Okay, which is to say, if there's an electron withdrawing group that's not on the same carbon, but kind of far away from that carbon, that thing will be more acidic. Or if there's a donating group, then it'll be less acidic. Okay. This is a rough order. This is like not a kind of fixed thing. It depends on each problem where how acidic or basic, like, or how these things will affect how acidic or basic it is, right? So for example, like charge usually doesn't come up as something in acid-base problems. Okay. The type of atom usually doesn't either, right? Hybridization will, resonance will, and the inductive effect will, right? And just a note on hybridization and resonance, these two sort of go hand in hand. So for example, like if we look at a structure like this, whoops, NH2. Okay. This is an amide. Okay. And a lot of the time people will think, okay, well, there's a lone pair. This is a primary amine. Okay. This lone pair is really unhindered. Like there's nothing getting in the way of it taking a hydrogen off something, right? So normally people will think like, okay, this is pretty basic. Okay. This is not the case though. So the structure actually isn't that basic. And the reason for that is because, let me use a different color. We can actually get, whoops, not that way. So we can actually get this lone pair to move over here and we can make a resonance structure. All right. And well, if we draw the resonance structure out this way, even though this is like the much less common form, or it's what we'd call the minor contributor of like the resonance structure, the fact that we're able to draw it this way, oops. The fact that we're able to draw it this way is that tells us that this NH2 has like, it's kind of sp3, it is kind of sp2. Okay. What that means is that this amide is way less basic than you would expect it to be. Okay. So because of this, oops. So amides are not that basic. Okay, this is a common thing that like trips people up. All right. Okay. Cool. That's like, well, that's like what I had to talk about. As usual, I've talked like a whole bunch. So we'll actually do some practice problems. If people have any questions, you can feel free to unmute yourself and ask, or you can send them in the chat or use like the raise hand feature or whatever. Otherwise, how about we start some practice problems? Okay. Yeah. All right, cool. Yeah, so like I said, I'm, let's see, I can copy and paste them. And so this normally takes like a moment. Oh wait, whoops. Oh, I accidentally pressed like the play button. I thought I heard someone talking. Instead it was Professor Molander giving a lecture. Here we go. Okay. Oops. Let me screen capture that. And all right, cool. And I'm gonna make a new one of these. Okay, here we go. And why don't I share or save this thing? Desktop, here we go. And one, save. Okay. Yeah, there we go. Now we're talking. Okay, all right, cool, there we go. We got the problem now. Okay, so here's the first problem. Let me move it up. Okay, if you're following along with the worksheet in that folder, here it is. All right, cool. So what does this problem actually ask for? All right, now we can do chemistry. So let's see what we're looking for. All right, so here's two huge drugs or steroids, or steroids are hormones, right? Yeah. Here we go. Yeah. So here's two big things. So let's circle and name the functional groups. How many pi bonds does each molecule have? And find and circle an aromatic ring. Okay. That sounds like fun. Okay. All right. So circle and name the functional groups in each of these molecules. All right. Let's see. Molecule one. Well, I guess you guys tell me what functional groups are there in the molecule. Shout them out or put them in the chat. Just like tell me what they are. Oh, okay. Oh, they're coming. Okay. Uh, oh yeah. Let's see. What do we have? So carbonyl. Oh yeah, that's a nice one. Oh geez, I can't spell today. Okay. Yeah, carbonyl, methyl. Oh yeah, triple bond. Triple bond. There we go. Yeah, we got alcohol, ketone, carbonyl, which, well, yeah, ketone or carbonyl. Oh my God. I already wrote carbonyl, whatever. All right, good enough. Uh, yeah, there's an aromatic and then triple bond or alkyne. Okay, yeah, okay. We named a whole bunch. Yeah, all right. Well, why don't I just start labeling then? Oh, there we go. Yeah, thank you, Amit. Um, yeah, nobody was saying that one. Okay, all right. So here we go. Here's an alkyne. Cool. Up here is an alcohol. Okay. Uh, OH is always an alcohol. OHs are really nice and useful. A lot of organic chemistry as a whole is about alcohol groups. Okay. Yeah, here we go. Here's a methyl. And actually, very conveniently, there's a methyl on this other molecule. Okay, methyl is usually or commonly abbreviated with Me for methyl. Okay, there's a couple of other of these like short abbreviations like that. We'll worry about them later. Okay. Oh, there's another methyl over here. Cool. I already labeled one. And well, you see that one. Okay. Yeah, here's one. So this is a carbonyl. You can also call it in this case, you can also say it's a ketone. Okay. And let's see, is there also an amine? So up here, this is what we're actually working with. So this is an amine. It's not an amide. So it's an amine. Amides have to be attached to carbonyls. Okay. Um, doesn't seem like a huge difference. It turns out it really is. So uh, that comes like 8 months down the line. So don't worry about it too much. But just for now, remember that amines are just nitrogens and amides are carbonyls. Okay. Uh, that's like a kind of tricky, annoying thing. So amines are when you just have a nitrogen and you can have anything attached to it. Well, anything except carbonyls, right? Um, yeah, there are probably some other functional groups that are like nitrogen and something else, right? Like, and it might have a specific name, but whenever you have a nitrogen that's attached to either carbons or hydrogens, it's going to be an amine. Okay. Uh, yeah. Right. This is sort of like, oh no, this one's pretty specific, right? Like if there's a carbonyl, it's an amide. If there's no carbonyl, it's going to be an amine. Um, when you have things like carboxylic acids, right? Like, and this actually, Nidhi just asked a question about like if you have an amide, do you count the carbonyl twice or is it implied? It's implied, right? So like when you have, for example, a carboxylic acid, yeah, you could say like, oh, it's a carbonyl that's within a carboxylic acid, but like you don't usually say that, right? It's a carboxylic acid. Um, is yeah, that's usually what you say. Okay. Yeah, that's I think we got them. You could also say that like these guys over here, you can say like, oh, these are alkenes. Uh, or like if you want to be really like technically specific, I think the right term for the functional group itself is alkenyl, I believe. Right. So that's like the double bond itself as like a functional group. Um, that's more specific than you probably need. You can usually just write I think you can usually just write alkene, and like nobody's gonna have a problem with that. Okay. Let's see, what's the difference between a carbonyl and a ketone? The carbonyl is the thing itself. A ketone is when you have carbons on either side of it. Okay. So for example, like, here we go. Good questions in the chat, by the way. Okay. So here we go. Let me even use, let me draw this a bit nicer. Okay. So here we go. So this right here, this is the carbonyl. Okay. I say carbonyl. Some people say like carbonyl. I think it just depends on like where you're from. It's like one of those things how like people in the north say soda and then people in the south say like pop or whatever. It's one of those things. I don't know. Okay. Anyway, that's the carbonyl, and then this whole thing. And well, actually, there can be, let's say there are like other bonds, right? We don't care about what's on these carbons, right? It's just these two carbons. This is the ketone. Actually, okay. This blue circle is really bad now that I drew in the other bonds afterwards. So okay, here we go. Okay. So here's these other bonds. Yeah, now this part is the ketone. Okay, on the far right of the second molecule, is that an amide? Yes, it is. How would I even just label it? Why don't I just do this one in blue? Okay, this bad boy right here is an amide. Okay, amides are like amines, except, well, they're like it, except they have the carbonyl. Way later in the course, again, like way later, you'll see what amides and amines actually do. For now, be happy that you don't have to deal with them because they're very complicated. So, yeah, this is fine. When you have an aromatic, is it implied that it has alkenes? I would not call them that. The double bonds in something that are aromatic are like very much different from the double bonds that you have like a standalone double bond. This is, again, something that like comes up like way down the line. I'm saying that a lot today, right? But it's like the first workshop and you just started the course. The double bonds that are in something that is aromatic, like the whole something being aromatic like has a whole meaning on its own, and the double bonds there act like differently than a typical double bond would, right? So for example, you will see like in this course, like relatively soon, within a few weeks, and some of you might have seen this before in like Gen Chem. If you take something that has like a normal double bond and you put it in, let's say, bromine, then the bromine will go on both sides of the double bonds and turn it into a single bond. If you have something that's aromatic, that doesn't happen. Okay, so like aromatics are more like stable in some sense, but again, don't worry about this so much. Okay, do you classify the 3 6-carbon rings in the first structure as cyclic molecules, not aromatics? They're not aromatic. Okay, for the sake of right now, or for the sake of like Chem241, really, the only aromatic thing that you will see, or that you will be expected to know is aromatic, is this guy here. Okay, and this group on its own, this is called, I write R here to mean that anything else could be on the, over there, right? And then this group here being attached to something is called phenyl. This is a phenyl group. Okay. Yeah, you can actually call this as a functional group if you want. It's not very functional because, well, for the entirety of Chem241, you're not going to be allowed to do anything with this because the reactions with it get, more complicated. But you're welcome to call it a phenyl group and write that down. let's see this other structure. Okay, I mean, well, we've already named some of the things here, right? So let's, oh, I used blue over here, didn't I? Yeah, okay. So let's name these, okay? Here's an alcohol. There's another name for alcohol. Does anybody know it? Yeah, there we go, hydroxyl. Yeah, so you could call it hydroxyl if you want. I don't think anybody's gonna get on your case if you call it one way or the other. Okay, over here, there we go, it's an amine. Oh, let me actually, here's another alcohol, right? Let me point it up there. So here's an amine. There's a carbon ring attached to the amine in the first structure, aromatic. Yes, it is. It is aromatic. Well, yes, it is. Don't get hung up on the term aromatic. So in general, if you have 6 carbons and 3 double bonds in it, that's aromatic. Okay, for the sake of like this course. Yeah, that's all that there should be. So for example, in this other structure, here's 6 carbons with 3 double bonds. So this guy is an aromatic ring. Okay, that's not really a functional group, for example. Like phenyl, you could write down because like this is a, you know, this is its own group, right? With nothing else attached. Like that's like we have a name for it. We don't have a name for this thing attached with 4 things over here. Like, so it is aromatic, but I wouldn't call that like a functional group so much. Okay. Over here, yeah, here we go. We actually have another amide. Okay. It's a nitrogen, it's attached to a carbonyl, that's an amide. All right. Even though this nitrogen has like no hydrogens on it or whatever, it's connected in this huge ring thing. It's there's an amide here. Okay. And then we have double bonds. I'm not going to fill those in and label them because this is already complicated enough. Okay. Anyway, what have we actually been working with? So anthromycin. Well, it's likely that a lot of you who are taking this course are pre-med, so you might know what that is. You might have no idea. So it's an antibiotic, and just for the sake of like things being interesting, or just for the sake of making this like molecule more interesting than just some random molecule we picked. So it's an antibiotic, and while I'm not certain about this, the most likely part of it that is active is this amide here. Okay, and the actual reason for that is because this amide is very similar to an amino acid. Okay, and amino acids look like this, and then they have a whole bunch of other stuff, and this repeats over and over. Okay, and so this part here, like the rest of this molecule is just to help the thing fit in to the spot where it's supposed to look like an amino acid. Okay, and this is the part that actually does the recognizing. Okay, this is the part that tricks, like in this case probably like the ribosome or whatever of bacteria, right? If you're not like pre-med or you don't care about biologically related chemistry, I'm sorry, you maybe that was like totally irrelevant to you. But yeah, all right, cool. Okay, well, we've marked these up. Why don't I even just copy and paste in this thing all over again? Just because it's kind of messy as I have it. Okay, and let's see. The next thing is about pi bonds, and then what we got something about aromatics. Okay, we've already talked about aromatics a whole bunch, so we already know that. Let's say C. All right, so C. Here's an aromatic. Here's an aromatic. Okay, 6 carbons, 3 double bonds. That's going to be an aromatic for the sake of now. Okay, well, as long as it's in a ring. Okay, it has to be in a ring also to be aromatic. It's a whole thing that comes up way down the line. But if you see something that looks just like this, then you can call it an aromatic without worrying, right? And okay, how many pi bonds does each molecule have? All right, well, pi bonds only show up when you have a double or triple bond. Okay, so we don't have to worry about any of the hydrogens on any of these structures, right? They're not, those aren't going to affect us because you can't make a double bond with a hydrogen. Okay. Let's see, how many pi bonds does each molecule have? All right, well, this is one of those situations where you actually just go through and count. All right, so here we go. 1, 2, 3, 4, 5, 6, 7, 8. There's 2 here because it's a triple bond, right? So you count everything after the single bond. Okay, did I miss any? No, I hope not. All right, so this one has 8. Okay, if I missed one, yell at me. All right, here we go. 1, 2, 3, 4, 5, 6, 7. And okay, 7. Okay. And so someone's asking if we should count the ones that are, or that could be there in the aromatic ring. So I guess meaning like, so you, well, there's 2 ways that you can interpret that. So either you mean, yeah, with resonance, right? So you can move these 3 bonds around and you'll get 3 different double bonds. I wouldn't count that. Just count them as is in the structure. And there's actually also another form of resonance here that you could do. So here, this nitrogen looks like this, right? And well, it has a lone pair, right? It's not drawn in there, but if you're doing the octet rule, then there has to be a lone pair there, right? And well, this lone pair can hop over here and these electrons can hop onto that carbon. Now it's a different structure, right? But there's still going to be 3 double bonds. Also, I don't worry about that. And just when it asks for something like this, how many pi bonds does each molecule have? Just go with the structure that's drawn, probably. Yeah, maybe in this example, it wasn't that interesting because like, in this case, it stays with 3 double bonds the whole time. But for example, when you have this carbonyl and these 2 double bonds, they're what you can call all conjugated, meaning that you can move these electrons around, right? So I'm just drawing the part of the structure here that's relevant. Really, it's within the whole much larger thing, but for the sake of this, I'm just drawing the part that actually matters. All right, so you can move these electrons down here. Nothing is stopping you from doing this. Okay, and yeah, now this gets ugly, right? Because now you've changed the number of double bonds. For the sake of like answering this question, just do it as drawn, right? Just use the structure as it comes up. Okay. All right. How about we move to question 2? Normally, while I like paste the question, that is like a short time where you can write questions and ask or something, because I have to copy and oh yeah, there we go. I don't know why it has a weird shadow effect, but you know what? That's okay. Yeah, there we go. All right, draw the important resonance forms. Okay. And determine which are the major contributors. All right, so let's see. All right, A. Okay, well, we've got a plus charge here, and we have these triple bonds, and like, let's say, here's that pi orbital, so, well, we can move this double bond over there, right? There's nothing in the way. There's no, like, for example, there's nothing that's sp3 between that plus charge and those double bonds, so it's okay, right? If there was, then it would be off limits. But all right, well, we can do that. So we can move them one at a time, right? Drawing resonance structures can be tedious because, well, you kind of just go through them one at a time. But if you go through them one at a time, you're much less likely to make any errors. Okay, so there we go. And well, let's move that one over. So I'm going to draw these in like a weird, in weird positions just because I don't want to like get in the way of this next problem. All right, well, okay, so we moved it over and we've moved it onto this bond. So now the plus charge falls onto here. And all right, well, let's move that bond over. And drawing 7 carbon rings is like a pain. 6 carbon rings, like you'll be drawing over and over, so like you'll get really used to that. 7 carbon rings, not really. If you get 8 carbons, it's a stop sign, which is like really nice, but this is just a pain. Okay, well, here we go. Okay, and we can move that over, and well, now we're 1 off from the carbon that we started on, right? So we can keep going. We can move this over. Okay, and it'll land on a new carbon, one that it hasn't, the positive charge will land on a new carbon where it hasn't been before. Okay, and you can keep drawing those, and what you'll find is that there's 7 total resonance structures because it can land on each of the 7 carbons. Okay, that's a lot of them. It's going to be the same thing over and over again, so I'll leave the remaining 3 of them up to you. All right. But what you find is that the plus charge lands on each of the things, right? The thing with resonance structures to note is that they're not like, it's not like the molecule is either in the first state or the second state or the third state, right? It's in a mix of all of them. So what you really find is that the positive charge is on all of the atoms, okay? It's kind of like on all of them at once. All right, and so one way that people draw this, people will write like a plus charge here, okay? And, oops, there we go. Let me get that better. Yeah, so some people, in a case like this, will write like a plus charge, and then they'll draw a big circle, okay? Which is to say that everything else is filled with double bonds. Okay, this provides all the information that you need. You might also see with benzene, and I've been trying not to do this earlier, but a lot of the time, since benzene, you can just move the bonds back and forth. Frequently, people will draw a hexagon with a circle in it, okay, which says that. All right. You don't need to worry about this too much. The more important part is that you can draw all 7 of these resonance structures, which is just doing it over and over. Okay. All right, next one. So what do we have? We have a negative charge on here, and it's next to these double bonds, which means that we can probably do something over here. Okay. So, well, let's go for it. And we can take this negative charge and move it right there onto that bond and kick this guy over to the carbon on the end there. Okay, even though there's double bonds within the structure, because there's a positive net charge, that would still make it reactive. Yes. This thing, so this is about this previous problem that we just did. Yes, this thing is reactive. There's a name for it. It's called like the tropylium cation or something along those lines. I can't remember the exact name. But yeah, you could do stuff with this. In fact, this ion is like really stable. Because that positive charge is over 7 different carbons, this thing is pretty stable. From what I remember, you can actually like store it as a salt, like at room temperature or whatever. And it's like totally fine and normal. But it will react with stuff. Yeah, so you can use it for stuff. You don't really do much reactions with it. You just see it down like eventually, because it's like a common example of this sort of like resonance. Yeah. Yeah. Reactivity comes like, well, I mean, you'll get to reactivity soon enough. So I guess like, you know, you'll get to see what's reactive and what's not. But with something like this, you probably won't really get to work with it or play with it for a while. Yeah. But it's a good example though, because like I like to kind of see it in these examples of like stuff that you'll see down the line. And then, you know, maybe in like 6 months, you'll think like, oh yeah, I remember that first day of workshop where we had that weird thing, and look, it's here again, right? I don't, nobody's going to do that, but like, you know, if you get to see these examples early on, then when you see them like later, when they really matter, or when you're really using them to do something, then you'll be more comfortable with them. Okay. All right, here we go. So, okay, we're moving these guys over here. Instead of writing C or H2C each time, I'm going to replace it with just the end of this. I'm not going to write it in. Okay. Yeah. So here we go. And we moved this. Whenever you're drawing stuff like this, don't pick up or lose any carbons. And like, maybe it seems silly or maybe it doesn't, but like if you're worried that you picked up or lost carbons, and I do this like all the time, like this is, you should, if you're ever like unclear about how many carbons you have, just number them. Okay, here we go. 1, 2, 3, 4, 5, 6. We have 6 carbons long. Okay. And what I just drew is 1, 2, 3, 4, 5. Oh wait, okay. I actually didn't even mean to do that. But I forgot one. Okay. I swear that wasn't staged. I promise. I guess because I started talking about numbered carbons before I finished drawing the structure, right? Also, this part of the molecule doesn't really matter, so I guess I wasn't paying attention. All right. Well, anyway, let's finish drawing what we had. So there's a minus charge here now. All right, and well, we can actually move it onto here. But if we're gonna do that, then this carbon will wind up having 5 bonds on it. So we need to kick these guys up to there. Okay, and let me draw another wall. Here we go. Right, double bonds. And now that oxygen has a minus charge, and okay, I drew all my carbons in this time because now I actually remembered. Okay, that's it. You can't do anything else, right? Again, this whole part of the molecule here is irrelevant because it's all single bonded, so you can't do anything with it with resonance. Okay, and that's the only spots that you can put that minus charge. You can't do anything else with it, right? So you're just going back and forth between these. Okay, here we go. What do we have next? Can you explain? You move the electrons to carbon 3 and not a double bond to carbon 4. Let's see. So what I did here was, you can move this minus charge to fill in a bond that it's right next to, right? So first I moved it to this bond between 1 and 2, and you have to kick this double bond off to a carbon that it's also attached to, okay? It can't skip over to the next carbon. So for example, this double bond in the first step, it can't hop over to 4, or it can't hop between 3 and 4. Well, okay, yeah. So going step by step, then we have the double bond between 1 and 2. We have this minus charge on 3 and then up here, right? And then we can move the double bond to between 3 and 4. You can also, in general, if you can write resonance structures, you can probably write them in fewer steps, right? They'll typically ask for all resonance structures, in which case do what I just did here, okay? They might, well, if they don't, for example, and you're like, you know, you're at the end of Chem242 and you're like, I don't want to continue to keep writing all these out. I've been doing this for too long. I just want out of this course, right? What you don't have to, right? So usually there's a way to, let's say you have a structure like this, you can usually go from one resonance form to another much faster in fewer steps, right? So you can move multiple things at once. So move this guy over here, move this up here. Here we go. And now we've got, whoops, that's not even supposed to be a double bond. Okay, and now we've moved this up here. Okay, so you can do it in one step, right? And well, there's nobody saying you can't, but when it comes to actually solving these problems at this stage in the course, you'll want to go step by step and do them one at a time and show all of them. All right. Maybe just to tease Chem242 a little bit more, something that looks like this, you will see again down the line, right? I keep saying that, and I will keep saying that, but maybe that's just to stress, like, these structures that you're seeing now will come up again. And it's good and important to see it. Are there only 2 resonance structures for B? Well, there's 3, right? It's just one of them was already drawn for us, so we didn't have to do it ourselves. Okay, there's 3 resonance structures, just 2 that you had to draw. Yeah. Okay. We have a resonance structure where you keep the negative charge on the first carbon, but only move the double bond oxygen negative charge. Oh, so I think what that question is asking is, like, can you basically take something that looks like this, and could you, I guess, if you wanted to do that, you would have to do something like, well, you could just move this double bond up, right? And if you did that, well, yeah, you would get this, right? With any carbonyl, you can always move the double bond up and you can have this polarization. For a problem like this, you don't want to have this much charge, okay? If there's 1 charge in the molecule, you'll probably want to keep it as 1 charge. If they give you a neutral thing and they say, like, oh, draw the resonance structures, then yeah, okay, you can split charges and you can, and then you could do some interesting stuff with it. But for something like this, where there's just a minus charge already, you could just keep that 1 minus charge and not worry about all the rest of the stuff. Okay. Yeah, these are good questions, guys. Thanks. And if it's like, if there's some time where it's just easier to, or if it's like a long question and you don't feel like typing it out, I mean, I'm really lazy. I don't like typing that much. So, like, if that's you, you can always unmute and ask. Either way is fine, right? I have the chat open, so fortunately, I've been keeping an eye on it. Okay, here we go. So let's see this structure here. All right, we have a plus charge over here, so that's what we're working with. All right, and first thing we can do is move the double bond over. Right, we can work with that. Oh, okay. So someone's asking how do we identify major contributors? Okay, in this first problem, none of them are any better than the other, right? They're all the same. In fact, you could just twist the molecule and it would look the same as what you started with. So they're all, I guess they're all major contributors, right? They're all the same. Okay. In the second one, well, determining what is like more stable or less stable depends on like where the charges fall, or, well, I think it will only really depend on where the charge or the radical will fall. Okay. So in general, so a positive charge is more stable on a tertiary carbon, okay? So which looks like, oh, let me draw it like this, okay? So this is more stable than something that looks like this, which is secondary. which is more stable than something on a primary, right? Okay. And negative charge is the opposite. Okay. The exceptions to that is that both plus and minus, I'm writing them in circles now. It's really common when you're drawing the structures to put them in circles. So both positive and minus charges are more stable when they're on either benzylic carbons or allylic. Okay. So they'll always be more stable on one of those two. Okay. That's if you're dealing with just carbons. If you're dealing with other atoms, then you'll want to think about electronegativity. So if it's not just carbons, then okay. So you'll want to think about electronegativity now, right? So in like, let's say in the case of B, oh, and I guess the question asks also to identify the major contributors. So kind of relevant, right? So in the case of like B, here the minus charge is on carbon. Here it moves over to carbon. Okay, that's no better one way or the other. Here it's on the oxygen. Okay, and oxygen is more electronegative, so it's more happy. It's it's more okay with having a minus charge on it. So this one is like the happiest in some sense, you could say, right? To anthropomorphize molecules, because the minus charge is on the most electronegative thing. So this is the major contributor, and this is minor, and this is minor. Okay, both of those are minor contributors. All right. Okay, here we go. This next one, we were moving this double bond over. So let's actually do that. Yeah, minus charges are more stable on primary carbons than secondary carbons, and least stable on tertiary carbons. Okay. So here we go. If there's a positive charge moving around, is it stable on the least electronegative? Yes. Yeah. Right. So if there's like a nitrogen, if there's a nitrogen and an oxygen, for example, the positive charge would be happier on the nitrogen. For part B, even though the major contributor exists, you still count the overall molecules having a carbonyl. Yeah, sort of. In this case, it's kind of like complicated because this molecule can do some interesting stuff, to say the least. Yeah, remember that it's in a mix of all of these three, right? Like, it has a little bit of character from each of them, each of these three resonance contributors, which is like the vaguest thing that I could possibly say. But yeah, we would probably say in general it has like a carbonyl, right? Because one of the characteristics of a carbonyl is having the positive charge on the carbon, having the negative charge on the oxygen. So in this case, you could say it. I haven't ever seen a question where they ask like, draw the resonance structures and identify the functional groups. At least not when the functional groups can change in the resonance structure, right? Like, that's kind of, there are some functional groups that don't change at all. They're unambiguous, right? But in this case, they do. So they likely won't ask something like that. All right, here we go. There we go. We've moved that. Okay, let's move this guy now. Okay, we can move that double bond and sit here and redraw the thing. I'm going to draw this lone pair on the nitrogen because, well, I am guessing it's going to be relevant. Okay, there we go. There's those double bonds. Okay, yeah, here we go. That nitrogen is relevant, in fact. So we can move those electrons and keep going. This nitrogen now has a positive charge because it really only has 4 electrons that it can call its own, but nitrogen's like to have 5 normally. Okay, so now there's that plus charge, and well, let's see. Can we do anything with either of these oxygens now? So let's see. We can't move these guys over to here, can we? No. This nitrogen would have 5 bonds. Okay. So we can't move these electrons down to here, right? The nitrogen can't give up any electrons because it has a positive charge. It's missing electrons, right? So it's not going to give any up. Okay. This oxygen with the lone pairs, well, yes, it could give its lone pairs here, but then it would, this nitrogen would have 5 bonds again, right? So we'd have to lose something else. Okay. So this seems like it. These seem like the 4 that you can really do something with, right? In terms of which is the major or minor contributors, well, okay, here there's a positive charge on a carbon. That's not good. In fact, it's a primary carbon too, so that's extra not good, right? Here we go. There's a positive charge on a secondary carbon. No, not much better, right? Tertiary carbon. Okay, now we're getting somewhere. But well, yeah, and then here we have this positive charge on the nitrogen, right? And well, let's think about it. Nitrogen is more electronegative than carbons, right? So nitrogen would rather not have that positive charge. So, okay, then I think that this one would probably be the major contributor. Okay. I think that would be it. Okay. Anybody have any thoughts? Disagree? You don't have to agree. Doesn't it break the octet rule? Oh, yeah, you're right. Oh my God, yeah, you're right. Okay. Yeah, I was trying to think. Yeah. Oh, I forgot about the octet rule. Yeah, okay. That was sort of like an implicit thing that I was thinking about. Yeah, okay. That is a good point. Octet rule probably comes first here. So in that case, this one probably would not be as significant. I was writing those ion things for like when you have primary, secondary, tertiary, all those carbons. Yeah, those things usually apply when you don't have something dealing with octet rule. Yeah, if you can satisfy octet rule, then you want to do that. That's usually like the best or most preferable. So okay, yeah, you guys are right. Thank you for pointing that out. So this is major contributor because octet. Okay. Yeah. And we can't do anything else after this because otherwise, yeah, we would have 5 bonds. And well, that's not okay. Okay. There are things that can have 5 bonds, but well, for now, let's leave those alone. Okay. All right, here we go. Last one. Oh, let me cut through here. Okay, cool. Oh yeah. Here we go. Oxygen and it's attached to this phenyl ring and okay, we got this NO2. All right. So let's start off. Let's move these guys over. All right. And here we go. Here's O. this double bond stays, this one stays, this one becomes a minus. And then, well, we're gonna probably just want to write this NO2 out while we're here. Okay, so the structure of NO2, you could do out the whole Lewis structure formulas or whatever. I totally don't remember those. NO2 is one of those things that like you usually just write it as NO2, but like one or two times you'll have to actually draw it out. So in this case, I just remember what it is because like it's easier than having to solve the structure of NO2 every time. So this is what it looks like. It's probably good to just keep that in mind. Okay, so here we go. Let's go back and forth. All right, arrow. Oh, I didn't even draw what I'm doing. What's up? Yeah.
When drawing resonance structures, do you have to like draw the two NO2 resonance structures? Like would those count as like two separate resonance structures, even if it doesn't necessarily like contribute to the rest of the molecule's resonance?
In this case, you probably don't need to, because that doesn't really tell us anything. The reason I drew it out,
the oxygen to have like the negative charge on, just for like writing it.
What was that? Sorry, I didn't hear.
So it's fine to just pick one of the oxygens to have the single bond and the negative charge on, and you just like assume that it's like localized between the two.
Yeah, if they're gonna ask you a question like this, it's probably because there's something more interesting going on than that NO2, right? Okay. So like, yeah, moving that minus charge back and forth, it is a resonance structure, but like, you'd probably lose points if you did something like that. Like that's not what they want normally, right? There's usually something more going on.
All right, sounds good. Thank you.
Yeah. The reason I did draw out that NO2 is because something gave me the feeling that it would be interesting. It would actually get involved in what's going on here, right? So, well, let's keep going, right? Okay, this double bond now has to hop over, and oh, now it's on that tertiary carbon. That's like the worst place for it to be, but okay. On the bright side, though, we have a plus and a minus charge right next to each other, so hey, we can actually do something with that. And let's move that over there, okay? Problem though, this nitrogen now has 5 bonds if we move this over here, okay? But we can push these electrons onto the oxygen, and here we go. Now we're talking, okay? Now we've got something like this, and oh yeah, double bond there, and O minus, and well, looks like this nitrogen still has a plus. Let's see. Why wouldn't they write the positive charge on nitrogen in the structure given to us if it was bonded to those oxygens in a way that would make it have a positive charge? The reason they don't do that is because this NO2 here, as a whole, it has net charge 0. Okay, so let me do this in blue. Here we go. So this thing over here, which is this over here, has a net charge of 0. Okay. Yeah, so since they condensed it down, they don't write the all of the charges on everything. That's like, I mean, I'm kind of with you there. I think that's also kind of annoying. There are some cases where they do this. It's not it doesn't happen very often in this course. In fact, this is probably like the main place that it does. But for example, every once in a while, you'll see something that's written like, you know, at some point you'll like way down the line, you'll see sugars, which can be written like this. And then they can have like, oh yeah, here's PO3. PO3 like H minus or something like that, right? And you're expected to know that that looks like P something like this, right? O minus, right? Like, yeah. this is like maybe the one other case where this comes up. Otherwise, it doesn't really like. It's kind of just here, which is why I just remember what it is, and keep it in mind that way. Yeah. Okay. Let's see what we're working with here. So okay, here's a minus charge on the oxygen, and everything is satisfied. Everything is octet. So that's one thing we're working with, right? Here's a minus charge on the carbon. That's not as good. Okay. Let's see. Yeah. Okay. Here we have this minus charge on this tertiary carbon. Well, that's even worse. Okay. We definitely don't want that one. Okay. We can move the electrons over here, but somebody asked, why can't we just move the electrons here to make 2 double bonds and have it neutral? It would have 5 bonds. And 5 bonds is like, that one is not okay. Nitrogen, there are some things that can have 5 bonds, but nitrogen's not one of them. Okay. Yeah. So this nitrogen just can't become neutral, because the only way that it could is if it had 5 bonds, or if it wound up getting a lone pair, but then you'd have to do some funky things with the oxygen. We're not, we don't want to do that, right? And then over here we have this plus charge on the nitrogen, 2 minus charges on the oxygens. That's another option. Okay, so it's these 2 middle ones are definitely not major, because you have minus charges on the carbons, and that's not really good. Okay, over here you have plus on the nitrogen, 2 minuses on the oxygens. Okay, up here you have, there's a plus on this nitrogen, there's a minus on the oxygen, minus on the oxygen. Okay, so same ions. Okay. What I'll say though is that this one here, D, is more stable. So this is the major contributor. Okay. The reason for that is because this one here is aromatic. Okay. And again, this is this vague term, which like I'm, coming up with out of nowhere, and we don't really know how to handle yet. Because we have this ring with 3 double bonds, it is aromatic, and aromatic things are like super stable. Again, they're not very reactive. You're not going to be able to do anything with them for a while, right? For the sake of like this whole course, if any like question tries to say like, oh yeah, do this reaction onto the double bonds of the aromatic ring, you tell them like, no, get out of here. Okay. You like this arrangement of 6 carbons in a ring, 3 double bonds is very like energetically favorable, if you will. Okay. Whereas here, we've had to break that. Okay. This is a ring with 2 double bonds, which is like whatever. It's nothing special. Okay. It is what it is. It's a ring with 2 double bonds. But over here, this ring with 3 double bonds, well, for some reason, it's more special. Okay. It's somehow better. Right. What that means will be explained long from now, but for now, it is. Okay, so our aromatic's just a special case where the overall molecule is not reactive, even with pi bonds, double bonds. Electron rich, so overall more reactive. Yeah, so this here would be more reactive. This gets like into the whole like discussion of like what you can actually do with these molecules. For now, so yeah, I guess like this, if a form were to react, it would probably be more like this one, but it won't really, because it's really in a mix of all of these, and this is the major contributor, so it's probably not going to react very much anyway. This aromatic thing is just like is really so much more stable that it will be forced more into this like configuration. Yeah, reactivity with aromatics gets complicated. It's a whole big thing, and well, we've hardly even gotten to reactivity yet at all. So don't worry, I've got a lot more to say about it, but for now, it's better if we hold off on that. And then for 2C, why do we have more pi bonds in the last resonance structure? let's see. Are you counting it wrong? You're probably not counting wrong. Actually, in fact, you're not. The reason we have more double bonds is because this lone pair in the nitrogen, we started using it, right? Earlier it was just sitting as a lone pair, whereas in the end, we don't have any lone pairs just hanging around. We're using all of them, right? So here we have 2 double bonds and a lone pair. In the end, we have 2 plus 1, 3 double bonds. Okay. Yeah. Okay. Let's see. All right, got a little bit more space. What on earth did I press? Okay, here we go. Let me just save this thing. All right, cool. And let's make a new thing. Okay, and the last thing is about, let's see, here we go. Oh, whoops, I'm trying to find my actual worksheet. There we go. The last thing is about acidity of different stuff. So I wasn't like planning on going through all the problems this time anyway. We'll finish the problems next week, and you have the worksheet and all that. So yeah, I mean, since this workshop was about like 2 weeks of stuff and also 2 kind of important weeks, you know, it's fine. So in this case, it was asking which of the protons is most acidic. So here we go. Most acidic, all right, and well, what are we working with? Okay, so over here, again, it's very hard to compare in terms of like some sort of list or something, right? Like there's no real list that will work. But what we do know is that charge really, really affects acidity in basis theory, okay? So when something is positively charged, it's gonna be pretty willing to give up its protons like easily. Whereas these things will have to take on a negative charge in order to give up their protons, and they're not gonna wanna do that very much, okay? So that means that NH4 is gonna be the most acidic one. Okay, so this is more acidic than either of these two. And now with these two, well, we can actually think about what else there is going on. Okay, so over here, yes, we have this, we have just a plain NH, okay? And to do that, it'll have to take on a negative charge, and that's not great, okay? Over here, though, well, this structure is a little bit more interesting because, well, we can move these electrons. Remember I had said, like way back, that amides can do this thing where they can do this. Okay? And well, now we have a couple of effects going on. So for one thing, this amide is sp2. This is kind of sp2. Okay? Over here we had sp3, and this one is only ever sp3. Okay, so that's one thing. And then over here, it's also kind of positively charged, right? At least some of the time, it's pretty positively charged. So both of those things make this nitrogen more acidic, right? The hydrogens will come off more easily. Okay, which means that this amide here, I'm just gonna write amide, is more acidic, and that only leaves this last thing. Okay, so this amine is left. Okay, there we go. That's one of them. There's 2 more, which are good to practice. I'll also talk about them next time, just because I don't want to like talk forever. Okay, so if there are any questions about this one, this one was not as complicated as the other 2, I think. But if anybody has any questions or anything, like it's a Sunday, I'm just sitting here, right? So like, feel free to ask. I'll post the recording, and I'll figure out also where to put all the materials, so I'll like let you guys know about that. But for now, that is all we'll do today. Why don't I even Stop screen share. Oh yeah, there we go. Okay.